This is section 6.4 and 6.5, Triangle Inequalities. First part of this video is on inequalities within one triangle. So look at the purple triangle I've drawn there on the left. That triangle has two equal sides. AC and AB are both 12, so they are equal. So I know from the isosceles triangle theorem that since AC equals AB, then the angles opposite those sides must be equal. Angle B must equal angle C. What if I have a triangle in which I know two sides are not equal, like the triangle on the right? RT is 13 and RS is 12. So RT is definitely longer than RS. What does that tell me about the angles of the triangle? Well, it would make sense that if a side of a triangle is longer, then the angle opposite it must be larger so that it traces out a bigger side. And that's exactly what our first theorem says. If one side of a triangle is longer than a second side, then the angle opposite the first side is larger than the angle opposite the second side. So in the triangle I've drawn here, if I know that DF is greater than DE, which I've said here, DF is greater than DE, then I know which angles are involved here. So DF is there, the angle opposite DF is E. So angle E, and what do I know about angle E? Well, the other angle involved is the angle opposite DE, which is angle F. So according to this theorem, if one side is longer than the second side, then the angle opposite the first side is larger than the angle opposite the second side. So angle E must be larger, it must be greater than angle F, because angle E is opposite the larger side. If you want a shortened way to write this theorem, we could simply write it as longer side implies larger opposite angle. Very similar to that theorem is this one. If one angle of a triangle is larger than a second angle, then the side opposite the first angle is longer than the side opposite the second angle. So this time we're starting with angles rather than starting with sides. If angle E is greater than angle F, which side is opposite angle E? That's DF. And which side is opposite angle F? That's DE. How do they relate to each other? Well, DF is opposite the bigger angle, so DF must be bigger. DF is greater than DE. If you want a shortened way to write this theorem, it's larger angle implies longer opposite side. We had longer side implies larger opposite angle. Now larger angle implies longer opposite side. And this theorem we're actually going to prove, and it is an example of an indirect proof that we learned about last time. So an indirect proof means we start with assuming the opposite of what we want to prove. So if we want to prove that DF is greater than DE, then we will assume the opposite of that. What's the opposite of DF being greater than DE? Well, let's assume temporarily that DF is not greater than DE. If it's not greater than DE, then either DF equals DE, and then DF is certainly not greater than DE, or DF is less than DE, then it can't be greater than DE. So we have two possibilities. Case 1 is if DF equals DE, then what must be true? Well, we have a triangle in which two sides would be equal then. DF would equal DE, means the angles opposite those sides must be equal. So then angle E would have to equal angle F by the isosceles triangle theorem. Now that's a problem. We said EF was greater than angle E was greater than angle F, and we just concluded that angle E was equal to angle F. So that's a contradiction. That's good. That's what we want in an indirect proof. The other case is our other possibility, which is if DF is less than DE. Okay, well, if DF is less than DE, then we have a triangle in which one side is greater than another, and we can apply this theorem that says the angle opposite that side must be greater than the angle opposite the smaller side. So which angle is opposite DF? That's angle E. So angle E would have to be less than angle F, because DE, which is opposite angle F, is bigger than DF. But that's a problem. So we've reached two contradictions with our given statement that angle E is greater than angle F. In one case, we got that angle E would have to be equal to angle F, which can't be the case if angle E is greater than angle F. In the other case, we got that angle E is less than angle F, which is impossible if angle E is greater than angle F. So this was by longer side implies larger opposite angle. So now we can say in either case there is a contradiction with angle E greater than angle F. Because it can't be the case that angle E is greater than angle F and either one of these two things happens. It's impossible. So the assumption that DF is not greater than DE must be false. Therefore, DF is greater than DE, which is exactly what we wanted to prove up here. So that is a complete indirect proof in what's called paragraph form for this theorem. Both of these lead up to this theorem, which we'll call the triangle inequality theorem. It says that the sum of the lengths of any two sides of a triangle is greater than the length of the third side. So if I have any triangle I want, any triangle I stumble upon in the wild, and I take any two sides of that triangle, so if I take CE and ES, and I add those two sides together, this theorem guarantees me that that sum will be greater than the third side, CS. If I take a different pair of sides, and say CE and CS, and I add them together, this theorem says that must be greater than the third side, ES. And if I take the third pair of sides, CS and ES, and I add them together, this theorem says this must be greater than the third side, CE. Any two sides of the triangle, you add them together, must be greater than the length of the third side. Here's an example. If the lengths of two sides of a triangle are 3 and 5, then the length of the third side must be greater than what number, but less than what number. So we know two sides. We should be able to say a range for what the third side can be, knowing this theorem we just looked at. So let's say let x be the length of the third side. which is what we're interested in. We know that if I add x to 3, I need to be bigger than 5. That's the third side. Also, if I add x to 5, I need to be bigger than 3. Also, if I add 3 and 5, I need to be bigger than x. So that's same analogous inequalities I had up here. If I add two sides together, I need to be bigger than the third side. Well, if my sides are 3, 5, and x, if I take any pair of those and add them together, I need to be bigger than the third side. X plus 3 must be bigger than 5, x plus 5 must be bigger than 3, and 3 plus 5 must be bigger than x. So now we have three inequalities. And solving an inequality is like solving an equation. I need to get the variable by itself, so I subtract 3 from both sides, and x is greater than 2. Subtract 5 from both sides, and the middle one, and x is greater than negative 2. And 3 plus 5 is 8. So 8 is greater than x, which means x is less than 8. Now, if x is the length of a side, then it's always going to be a positive number. So x being greater than negative 2 doesn't really tell me anything. It's always going to be greater than any negative number because it's a positive number. So that's useless. But the fact that x is greater than 2 and x is less than 8 is exactly what I needed. The third side must be greater than 2, but less than 8. So it's somewhere in between. Could be 3, 4, 5, 6, or 7, or it could be a decimal in between those numbers. Alright. Part 2 of our video is on inequalities between two triangles. So this time I have two triangles, and I want to know if I can relate the sides and angles of those triangles, even if they're not congruent. So let's imagine this pair of scissors. And the two blades of the scissors are two sides of my triangle. And the third side is this gap formed by the ends of the blades that my finger is right now. These blades aren't changing length if I change the angle of the scissors. The outside of the blades stays the same. So if I have a bigger angle that they make, they trace out a bigger third side. If I take those two same blade lengths and shrink the angle that they make, they trace out a smaller opposite side. That's exactly the idea behind our first theorem here. If we take two identical sides and we just change the angle between them, that's going to change the length of the third side. So this really long theorem expresses that idea, and we call it the side-angle-side inequality theorem. If two sides of one triangle are congruent to two sides of another triangle, think the blades of the scissors. When I change the angle, I create another triangle. Those two sides, though, are congruent. But the included angle of the first triangle is larger than the included angle of the second triangle. Then the third side of the first triangle is longer than the third side of the second triangle. A lot of words to express what's a fairly simple idea, but an idea that's actually very difficult to prove, and so we won't prove it. In the triangle on the left, I've got AB and BC drawn in purple there, and those are congruent to ED and EF drawn in purple in the triangle on the right. And I see that they're congruent by the hash marks there. So I've got two congruent sides, two pairs of congruent sides. But the angles between them are clearly not congruent. Angle B is clearly bigger than angle E. So since AB equals DE, BC equals EF, and angle B is greater than angle E, these triangles are not congruent. They're clearly not congruent. This is not side-angle-side congruent triangles. But this theorem says then the side opposite the larger angle, side opposite angle B, which is AC, must be greater than the side opposite the angle of the second triangle, which would be GF. AB was equal to DE, BC was equal to EF, angle B is greater than angle E. So AC must be greater than DF. Clearly it looks that way in the picture, but this theorem guarantees us that that would be the case. Very similarly, we have a side-side-side inequality theorem, and the picture looks the same. If two sides of one triangle are congruent to two sides of another triangle, just like we had before, but the third side of the first triangle is longer than the third side of the second triangle. So now we're making a statement about the third side instead of about the angle that those sides make. Then the included angle of the first triangle is larger than the included angle of the second triangle. So MN equals PQ, NO equals PR. And now what we're given is that MO, which is here, is greater than PR. So maybe this is 10 and this is 6. MO is bigger than PR. What this theorem says is that the included angle of the first triangle, which would be angle N, it's the angle included by the two pairs of sides that we have congruent, is larger than the included angle of the second triangle, which would be angle Q. So angle N must be larger, means it must be greater than angle Q. These two theorems give us a way to relate the sides and angles of two triangles that are definitely not congruent. If we know that one side is greater than another side in a different triangle, and the angles opposite them, we can write as greater than. Here's an example. I've got two triangles, RSV and RTV. I know RS is congruent to RT, and I know angle 1 is greater than angle 2. So these triangles are not congruent. RS equals RT. We've even got the reflexive property with RV congruent to RV in the middle. But these triangles are not congruent because angle 1 is greater than angle 2. So what can we deduce? Well, since RS equals RT and RV equals RV, we are going to use the reflexive property. And angle 1 is greater than angle 2, then we know the side opposite angle 1 in triangle RSV, which is SV, must be greater than the side opposite angle 2 in triangle RTV, which is TV. Since RS equaled RT and RV equaled itself, I have side-angle side inequality with angle 1 greater than angle 2. That means the third side of the first triangle, SV, must be longer than the third side of the second triangle, TV. Here are your immediate practice problems. And you must draw all three pictures. Number 1, name the largest angle and the smallest angle of the triangle HIJ there. Number 2, name the longest side and the shortest side of the triangle RTS. Number 3, given that BC is congruent to CD, and angle 1 is greater than angle 2, what can you deduce? Which is just like the example I just did. Make sure you draw all three pictures, and that is the end of sections 6.4 and 6.5.